Hello everyone. So I'm Amrut and here is Chaitanya as well. So we are doing our project is based on data center driven fraud detection system for financial transactions. So yeah, this is the main agenda for today's presentation. We'll be covering all these sections soon. So coming to the project goals. Our goal is to build a real-time fraud detection pipeline using a data center style design. So we have producers to API gateway to Kafka to Enricher to Desperaptor and to decision engine. Each transaction is enriched with data from Redis and PostgreSQL scored with a hybrid risk model that mixes ML and rules. And it is labeled as allow, hold, or decline. We also use Spark to process historical data for continuous model retraining and build a dashboard to visualize scores, alerts, and metrics in real time. Now, coming to the software components, these are the core software pieces. So we have producers which generate synthetic or dataset-based transactions over TCP and gRPC. The fast API gateway is our front door. It validates JSON requests, checks an API key, rate limits clients, and publishes either to the Kafka transaction topics or to a DLQ for bad events. Then we have the Kafka as the main backbone with topics for transactions, enriched score, decisions, and DLQ. We keep partitioning and per account ordering so the same cards events are processed in order. The enricher consumes transactions, looks at recent activity in Redis and customer or merchant metadata in PostgreSQL and outputs enriched transactions. The risk adapter loads our ML models and optionally an external risk API to compute one combined hybrid score. Coming to the rest of the software components, we have a streaming and analytics layer as well. So the streaming job uses Apache Beam to read, score transactions from Kafka, window them by account, and raise alerts when there are too many or too large transactions. Alerts can be returned to Postgres query or just logged locally. The decision engine then applies thresholds and rules on the hybrid score, uses Redis for idempotency, and writes final allow, hold, or decline decisions, plus audit rules. So our ML pipeline uses Spark to batch process historic data from Postgres and keeps the models up to date. And the streamlit dashboard shows risk scores, flagged alerts, and system metrics straight from Prometheus. Now coming to the hardware component, all components run locally on a developer machine that mimics a data center node. Multiple CPU cores, Postgres, and Kafka on SSD storage and inter-service networking, giving realistic performance while staying lightweight. Coming to the architectural diagram, it shows this is the simple diagram which shows the full path, producers and gateway feed, Kafka, events move through enrichment, scoring, and decisions. Every stage logs results into an audit database, so we can trace exactly how a transaction is evaluated. Coming to the overall architecture diagram, we can see that it spans our actual component. On the left, you see synthetic producers and the rest gRPC gateway feeding Kafka. In the center are the enricher, risk adapter, and decision engine, along with the Beam streaming job and the Spark ML training path. On the right are the different PostgreSQL databases, Prometheus metrics, and the streaming dashboard that tie everything together. Now, coming to the interaction, we can walk through one transaction to end. The gateway receives a JSON transaction, validates it, and publishes it to transactions or to the DLQ. The enricher pulls from Kafka outputs it using Redis and PostgreSQL and pushes enriched transactions. The risk adapter reads those computes and the hybrid score and writes code transactions. Beam monitors scored transaction and produces windowed alerts into the alert history tab. Historic enriched data flows into Spark for batch featuring building and real-time model training. Finally, the decision engine consumes score transaction, applied thresholds, and rules, and outputs the final decision. So coming to debugging, to ensure reliability, we use detailed logs, SQL checks on audit and history tables, Redis health tests for deduplication, DLQ inspection for malformed messages, and live Prometheus metrics for throughput and latency. Makefile debug targets automate these checks so the entire pipeline can be validated quickly. Now coming to the demo, now Chaitanya will present the demo. I'll be stopping my share.
Hello everyone, I'm Chaitanya. Now I'll be demonstrating the workflow of the project. So first, I start the core infrastructure services required for the system. I run make Redis start to launch Redis using Homebrew, which is used for fast lookups and transaction deduplication. Next, I run make Postgres start to bring up the PostgreSQL database that stores audit logs, enriched data, and alerts. Then I start the Kafka message broker using make Kafka start, which enables real-time event-driven communication across all microservices. Once Kafka is running, I create the required topics using make Kafka topics. After the infrastructure is ready, I initialize the database with reference data by running make seed metadata. This seeds customer and merchant metadata tables with sample data used during transaction enrichment. Next, I start the API gateway using make gateway. This launches a fast API-based service that validates incoming transactions, enforces API keys and rate limits, and publishes valid messages to Kafka or routes failures to a dead letter queue. Then I start the TCP ingestion layer. I run make TCP server to launch the TCP server that receives raw transaction streams and forwards them to the gateway. In parallel, I run make TCP client to simulate real-world traffic by generating synthetic transaction at a configurable transactions per second rate and sending them over TCP. Once ingestion is running, I start the streamline processing services. I run make enricher full, which consumes raw transactions from Kafka, enriches them using Redis and PostgreSQL, and publishes enriches transactions to a new Kafka topic. Next, I trigger the machine learning workflow. I run make ML step 1 to train initial scikit-learn models and then execute the persist enriched transactions into PostgreSQL for historical training. Then, after that, it uses Spark to export features and retrain improved models on large data sets. Next, I run the risk scoring services, which uses make risk and consumes the enriched transactions, performs hybrid risk scoring using machine learning and rule-based logic, and also writes the results to the Kafka and the audit database. After the ML pipeline is ready, I start the Beam infrastructure by running make Beam expansion service, which launches the required Kafka expansion service. Then I execute the make Beam all, which runs the Beam streaming pipeline to consume scored transactions, compute windowed aggregations, and generate fraud alerts that are written into PostgreSQL. Then I start the decision engine using make decision, which applies business rules to approve, hold, or deny transactions, and uses the Redis database for idempotency and stores all decisions in the audit database. Finally, I launched the real-time monitoring dashboard using make dashboard, which starts a Streamlit application on port 8501. So here we can see the output of the dashboard. So this dashboard visualizes live transaction decisions and system performance metrics, allowing us to observe the full pipeline in action from ingestion to alerting and monitoring. Thank you, everyone.
Here coming to the learnings, while building the system, we learned a lot. Comparing TCP and gRPC gave faster structured communication. We scaled TCP client workers to control load and TPS. And also Spark batch preprocessing enabled near real-time memory training and Dockerizing all servers and made deployment consistent. Finally, integrating a Prometheus-based back dashboard gives full visibility to system health and performance. Thank you.